food restaurant operates both a drive-through facility and a walk-in facility. On a randomly selected day, X and Y, let X and Y respectively be proportions of the time that the drive-through and walk-in facilities are in use. And suppose that the joint density function of these random variables is as shown. Find the marginal density of X. Now, let's define marginal density. So when a joint density function of two or more variables is given, like in this case, this is a joint density function of two variables. So if the variables are continuous, then the probability function of those variables is called a density function. Okay. Then the marginal density of one of these variables is defined as the probability density of that variable alone. So right now, it's a function of two variables that define the density of both X and Y. But we may be at times interested in just one of the variables. So here, X was the proportion of people who go drive-through, and Y is the proportion who go walk-in. Let's say we are just interested in drive-through, so we wouldn't want to know that what's just the role of X with Y eliminated. So one analogy is that let's say you and someone else have a lot of joint assets, and the proportion that, let's say, if we take one particular asset, it's not necessarily that you own it half and half. You may be um, like having different kinds of proportions associated to each person. So sometimes one may be interested that, okay, I know what the joint assets of the two of you are, but I may be just interested in knowing the assets of one particular person. So in that case, we basically separate the assets of the other person and just keep the assets of the person in which we are interested in, and somehow try to figure out what the value of that one is alone. So the way we calculate a marginal density is, let's say in this f of xy here, they're asking just the marginal density of x. So the way we do it is that we integrate over all the values of the other variable, which in this case is y. So the same idea applies even if there were three variables, let's say x, y, and z. Then to get the marginal density of x, you would integrate over all the values of y and all the values of z, and thus eliminate y and z and be left with only the variable whose marginal density you want, which is x. So to get the marginal density of x, as I said, you will integrate this function over y. So the notation for the marginal density of x, let's even write it down. Marginal density of x is denoted by, so you do f subscript big X and then x. So this subscript big X means that you're talking about the marginal density of x from a joint distribution. Marginal density of x in a joint distribution, not joint, but joint distribution fx comma y. So fxy, if fxy is the joint distribution, then the marginal density of x is denoted by fxx. Okay. So let's calculate it in this case. F x is, so as we said, we integrate over all the values of the other variables. So in general, it's integration from negative infinity to infinity of fxy dy. Now, you may have wondered that why do we write this redundant thing in integration? We generally are integrating functions of x, so we write the function, we write the integral, and then we write this dx in the end. Yes, a lot of times it doesn't need to be written because there is no ambiguity as what the variable is with respect to which the integration is being carried out. But there are certain situations where it's absolutely necessary to write it in order to know which variables you're integrating with respect to. So now, for example, over here, this is a function of two variables, x and y. But as we mentioned, the integration that we are carrying out right now is with respect to y over all the values of y. So that's why this dy over here is very important now, because it tells us that right now, for integration purposes, y is the only variable, x is just a constant. So when you will integrate this, you will pretend as if x is a constant and y is a variable, because dy means y is the only variable as far as integration goes. So in practice, this the y values that really have the non-zero part of the function are 0 to 1, and fxy is 2 over 11, f5x plus 6y dy. And now you can pull out the 2 over 11. And remember, x is now a constant because of the dy, only y is the variable of integration. So 5x is a constant. So we know the integral of any constant with respect to y would be that constant times y. So the integral of 5x is just 5xy. And the integral of 6y is, now that's the proper integral, 6y squared by 2, because y is the variable of integration. Remember, if this was just an a, then the integral of a would be ay. In this case, a is like 5x, so the integral of 5x would be 5xy. Remember, in general, the integral of any constant is that constant times the variable of integration. Okay, so 0 to 1. And again, since all this business is for y, so we may specify that y is equal to 0 and y is equal to 1, because now we have an ambiguity as to which variable we are putting the values for. Okay, so that's equal to 2 over 11, 5x, right? Y is equal to 1, so we can even do 5x times 1, plus this is a 3, so 3 times 1 squared. And the lower limit is 0, so both of them would be 0 when you put in the lower limits, 0 plus 0. Because when you put y is equal to 0, this part is 0, and this y squared part is also 0. Okay, so this is now 2 over 11, 5x plus 3. And it's a function of x. We'll pick this one. So if you want to specify that it's a marginal density, then you write it like this. But in general, marginal density is just the probability density of x from here. So you can even give it a different name. That's why they are calling it g of x over here. And the x range is the original range of x. So it's correct. You could have, in a written exam, you can either write fxx like this, or you can make a new function and say g of x. Okay, so we found this to be 2 over 11, 5x plus 3. Find the marginal density of y. So now the same business. Let's say the notation for marginal density of y would be f subscript big Y and then little y here. And that would be, now you would integrate the x out of the joint density function. So in general, it'd be the integral from negative infinity to infinity f of xy. And in this case, x also goes from 0 to 1 over the non-zero part of the function. And now this integration is with respect to x, because to get the y density, you have to eliminate the x out, or that's the same thing as saying integrate the x out. 2 over 11, 5x plus 6y dx. So you'll pull the 2 over 11 out. And now the integral of 5x would be 5x squared by 2, because x is the variable of integration. And the 6y is a constant, so the integral of 6y is just 6yx. And now x is 0, and x is 1. So when you put x equals 1, you get 5 by 2 plus 6y. And then when you put it 0, you get minus 0 plus 0. Because this one has an x in it and this one has an x in it. They're both going to be 0 when x is 0. So you get 2 over 11, 5 over 2 plus 6y. Now it's a function of y alone. So 2 over 11, 5 over 2 plus 6y. Find the probability that the drive-through is busy less than 1/3 of the time. So now you see why it's important to sometimes know these marginal density functions. Let's do another page. Okay. So for the drive-through, we have x, right? X is the proportion of drive-through. So is busy less than 1/3 of the time. So we want the probability that x, so if it's busy less than 1/3 of the time, then we want x to be less than or equal to, or let's say less than 1/3. Okay. And you can use the one for the x. We have g of x is equal to 2 over 11, 5x plus 3. And you want probability. So basically you want probability x is less than 1/3. Find the probability. They're saying find the probability that the drive-through is busy less than 1/3 of the time. So we want the probability that x is less than 1/3. So if your required probability involves just one of the variables, then you can use the marginal density of that variable to do the calculation instead of doing the joint density. So now we can pretend that this is just a one variable situation. So you know, in general, this kind of probability is found by integrating over the whole number line. So x less than 1/3 means negative infinity to 1/3 g of x. But this g of x was applicable only for x between 0 and 1. Otherwise, it's 0. So it means he would break this up into negative infinity to 0, g of x, plus 0 to 1/3, g of x. This part is 0, because the function is non-zero only from 0 to 1. So 0 to 1/3, the function is 2/11, 5x plus 3. Pull the 2/11 out. The integral of 5x is 5x squared by 2. Integral of 3 is 3x. 0 to 1/3 equals 2/11. So 5 1/3 squared by 2 plus 3 times 1/3, and the lower limits will be 0 because x is 0. The lower limit, and both of these terms will become 0 when you substitute 0. So this simplifies, they want a simplified fraction, so we should be doing it without calculator. So 2/11, and then this is be 5/9 times 2 is 18. And this is a 1. So let's see. So 5/18 plus 1 is 23 by 18. So 2/11 times 23 by 18. To 1 times to 9 times. So that's 23/99.